Welcome to the second half of Calculus 1. First half of calculus, we dealt primarily with the derivative. We looked at increasing and decreasing. That was the first derivative. We looked at critical numbers, relative max, relative min, flat spot, which ends up being a point of inflection. Those were found using the first derivative also. And then we looked at concavity. And to determine the regions of concavity, we used the second derivative. When it came to optimization, we were optimizing a function, and optimal means the tallest y value, and of course that sits at the top of the hill, relative maximum. That would be a critical number. Again, we use the derivative. And we can optimize to minimize functions as well. That's the bottom of a valley. Again, another critical number, again, using the first derivative. So we use the first derivative extensively. We also use the second derivative for the second derivative test and concavity. Now, I want to take a step back, literally a step back, because what we're going to do now is go backwards. We're going to go backwards because we're going to introduce this new operation. It's called integration. And the first type of integration we're going to do is called indefinite integration. Now, when you integrate, which is a verb or an action, what you produce is the antiderivative. That's a noun. So we have the derivative, which is a function, f prime of x, and we discover what that is. It's a new function. We now have the antiderivative, which is sounds like the opposite of derivative. In fact, it means to go backwards, and I'll discuss how that works in a moment. So I'd like to define the antiderivative. We would say that capital F is an antiderivative of lowercase f of x. And interestingly enough, we don't use the prime notation, not yet anyway. They're just two functions. They have two different names. One name is capital F, the other is lowercase f. Capital F of x is an antiderivative of another function, lowercase f of x, when capital F prime is equal to lowercase f of x. So capital F of x, that's the one that will become the antiderivative. And I will show you techniques as to how to discover the antiderivative. But for right now, what I'd like to do is try to verify that one function is the antiderivative of another, and then I'll show you the techniques as to how to discover these antiderivatives, how to go backwards. Well, my question is this. Is capital F of x, which is x cubed, the antiderivative of lowercase f of x, which would be 3x squared. So we have two functions, and I'd like to discover whether or not capital F of x is really the antiderivative. Well, the proof is to do this. Is it true that capital F prime are u equal to lowercase f all by itself? So let's do this. The derivative of capital F, the derivative of x cubed, are u truly equal to the lowercase f of x, 3x squared? And so the answer is derivative of this is 3x squared, which equals 3x squared, and therefore it is true. So capital F of x being x cubed is a derivative of 3x squared. So I could ask this question. What is the antiderivative of, how about 2x? So now I'm not giving you the antiderivative. It's your job to find it. Now think about what the antiderivative really is. I could translate integration, which is the act of doing the derivative backwards. It's also called antidifferentiation. So it's an inverse function. It's a backwards function. And here's how it works. Integration and antidifferentiation are the same thing. But what I'm saying here, guys, is what was the original function that somebody took the derivative of to produce this? I'm not asking you to take the derivative of this function. That would be 2. That's not what we're looking for. The definition of antiderivative is this. If you take the derivative of the antiderivative, you should produce this other function. So here it is. If I ddx some original function, I'm producing this 2x. So f of x, the lowercase, is 2x. So what function do you think I had? Think about it. Without really doing any work, any techniques on this, I think you could probably reason it out. The capital F of x must have been x squared, because the derivative of x squared produces 2x. So let's test that theory out. Is it true? Are you the antiderivative? Well, this is always the way to check the antiderivative, and that is to take its derivative. The derivative of capital F of x has got to be this lowercase f of x. And so therefore the derivative of what you propose perhaps to be the antiderivative, x squared, is that truly equal to the lowercase f of x? And the answer is, once again, yes. Now, I want to show you that that's not the only antiderivative. So right now, we think this might be the antiderivative to this function 2x. And the reason being, because the derivative of this function is 2x. So you got to be careful here, guys. Be very careful. We're not taking the derivative of the 2x. That would be 2. We're going backwards. We're saying somebody had a function in their hands. You can't see it. Nobody knows what it is. They hit it with a derivative, and then they produced the 2x and handed that to you. So this is what's happening. Someone's taking the derivative of an unknown function and giving you the results. Your job is to roll it back and say, what was that original function? Now, I've got a proposal for you on this problem. The proposal is if the lowercase f of x, again, is 2x, and the idea is to learn what that original function was. See, here it is, capital F. We refer to this as the antiderivative. We don't know what it is, let's say. But the derivative of capital F of x should be lowercase f of x, correct? I propose something to you, and that is that maybe f of x was x squared plus 100. A different function entirely. It's different than just x squared, right? It's x squared plus 100. It's a different function. Is this the antiderivative of 2x? Let's find out. Okay, we're going to do a lot of checking on these antiderivatives, and the way to check is always take their derivatives. So we take the derivative of capital F of x, and the question is, are you truly 2x? Derivative of x squared is 2x. Derivative of 100 is 0. And yes, indeed, we have ourselves another antiderivative that is a success. So here is the result. The result is that constant could have been anything, right? So we need to take this into account. We might not know what that constant is. And so therefore, when you produce an antiderivative every time, you want to put plus c in the back to represent what we refer to as the constant of integration. Because that could have been 100, could have been 1,000,000, could have been 1,000. It's part of that capital F of x function, but who knows what it is? Nobody really does know what it is. So I need you to produce a constant of integration. So let's do another one. And I'm just thinking here, how about this one? Somebody took a derivative and got that. What was their original function? Well, I would imagine their original function was x to the fifth plus any constant that you like. We call this the constant of integration. That's what that is referred to as. And really, all your derivatives should, your antiderivatives should have that. So what do you get when you find the antiderivative? We call it a family of solutions because you don't really just get one solution. You get an infinite number of solutions. You get the primary algebraic result plus any constant you like. So it could have been x to the fifth plus 1, x to the fifth plus 2, x to the fifth plus 3, and then it all piles together. There's just a lot of answers, and they all... The thing is, we might want to discover exactly which one it is. And those are called particular solutions, when you can actually nail down the constant. When you can't figure out what the constant is, that's where we are right now, we call that a general solution. So what you got right here is called the general solution. Now, what I'd like to do is I'd like to show you the methods, the techniques that we use to find these antiderivatives, not by just inferring it as we have so far, but really discover it. And I want to discover the rules associated with this. So let's say we have a lowercase f of x. Something like this. What is capital F of x? The antiderivative. Now, for now, let's refer to this as y, and that's the prize. Want to know what y is. Remember, the definition of antiderivative is that the derivative of the antiderivative is what gets us lowercase f of x back. Now, by calling capital F of x y, we replace this with y, and we get that dy dx is lowercase f of x. We refer to this as a differential equation. And what it says is, nobody really knows what y is yet, but we sure know that the derivative of y with respect to x is this known function, which is up here. So let me write that down for you. dy dx is equal to x, f of x, which is 2x squared plus x. All right, now, our job is to really get to this prize, which is y, and how do we do it? Now, normally when we get to the prize, when we get to the thing we're trying to solve for, I always talk about peeling away the layers. Peel away the layers. We divide by things, we multiply, we add, we subtract, until finally we get the y isolated. So if you take a look at this, maybe the first layer that you might want to eliminate is this dx down here. I realize that dy dx is one solid feature. It is a noun. It is the derivative. It's not really supposed to be a fraction necessarily, but you can almost imagine multiplying both sides by dx. And what would have happened is that you would get a dy all by itself, and you'd have a 2x squared plus x and a dx over here. So the dx kind of moved over there, and that's a good place for it. We've got a lot of x's over here. But the prize remains right there. How do we get to that prize? How do we get the y? Well, you see this d. D stands for derivative. What we need a symbol for the antiderivative. Right now we don't have that. We keep talking about antiderivative. We know that it's capital F of x. Like, that's just the name of the antiderivative. It's the noun. But we need a symbol that represents the action of taking the antiderivative. The symbol that was agreed upon is called the integration symbol. And here's what it looks like. We rewrite the problem, and here's my job. My job is to get rid of this d. D for derivative, what do you need? You need the antiderivative, which is this squiggly symbol. This is called the integration symbol or antiderivative symbol. And it will do the job for you. It actually is the opposite of d for derivative. So what happens when the antiderivative integration symbol touches the d for derivative symbol? As you might imagine, it's like matter and antimatter. They cancel each other out. Now, if you've taken the antiderivative symbol on this side, you must take the antiderivative symbol on that side. Well, guys, at least we solve for y. But now what? Well, you're left with this antiderivative, meaning you got action to take. So far, we haven't done anything to 2x squared plus x. It's pretty much the same as it was at the beginning of the problem. So we still have action to take. Now, the properties of the antiderivative in many ways are similar than that of the derivative. Antiderivatives are more difficult when it's a fraction or multiplication, just like derivatives are more difficult when there's fraction or multiplication. Antiderivatives with sums and differences are pretty straightforward. You just do this action to each term separately. So let's start with that. When we have a sum or difference, we can actually distribute the antiderivative symbol. So we would do the in fact, let's distribute even this. It's almost like a distributive law. We want this and this and this all together in one package. Plus, now distribute them into that x. Okay, at least I'm asking for the antiderivative of one item all by itself over there, and then also one item over there. So with a sum and difference, you can do each one separately, so they don't interact with each other, which is good. And here's something critical that I want you to notice. Do you notice that antiderivatives always have a little differential on the back end? And when the independent variable is x, it will be dx that will be sitting on the back end. See, same here. Antiderivative has a dx on the back end. So apparently, these things come in pairs. You cannot do an antiderivative without a corresponding dx or a dt or a ds, something like that. This is also similar to derivatives. Think about your derivatives for a moment. It's dy over dx. dy over dx. And the dx is simply there to remind you, hey, remember, the independent variable is x. That's why it's there. So what's it doing now? Same thing. Hey, remember, the independent variable is x. Hey, remember, the independent variable is x. So is it a big surprise to you that it sort of looks like it's multiplied out there? It shouldn't be, because derivative says dy over dx. Everything should be opposite, so now it's kind of times dx. Without that dx, it is not a correct integral. So please make sure that you use these two things like bookends. They really go together. Now, I've got some great news for you regarding constant multiples. Just like derivatives, constant multiples are along for the ride. I recommend that you drag them out front. I recommend that you drag constant multiples out front. Just let them sit out there. They're along for the ride. They're not zero or anything like that. And they'll be there for you when you're done with the actual calculus, the integration. Here comes the actual calculus. Now, if you were to take a derivative, I know what you would do. You would take this exponent, bring it down in front as a coefficient, and you would deduct one from the exponent. Well, if that's the act of taking a derivative, and the antiderivative is like the complete opposite, I don't think we'll be deducting one from the exponent. I think we're doing the opposite. We're adding one to the exponent, and that's exactly what we're going to do. I don't think that exponent is going to drop out in front and multiply. No, we're going to do the opposite. We're going to divide by the new exponent. So that's exactly what we're going to do here. Now remember, the 2 is along for the ride. So how does integration work on exponents? We add one to the exponent. Now, do we multiply? Do we drop this out in front and multiply? No. We divide by the new exponent, like that. And that's how you integrate. Now remember, every time you integrate, you always produce a constant of integration. Every single time we produce a constant of integration. So that's what happened over here. Now, over here, what power do we have? Well, this is x to the 1 power, so the antiderivative looks at that and says the rules are that you add 1 to the exponent and you divide by the new exponent, and we'll produce a different constant of integration, C2. So we do have two different constants involved here. Let's multiply this one out. This is 2x cubed over 3 plus 2 times whatever that constant of integration was, x squared over 2 plus C2. Now what do we do in the end here? Well, let's get the x's next to each other. 2/3 x cubed plus 1/2 x squared, that's this one, plus all this stuff. Now, I want you to think about what's going on over here. C1 and C2 are just constants, and they can be any constants that you want. They're called the constants of integration, and they can be anything. What happens when you multiply and add constants together like this? You just produce some other number, right? Like, you know, if this was a 5 and this was a 3, this would be 13. If this was a 1 and this was a 7, this would be 9. So basically, this gets all lumped together into one big constant. Because in the end, when you select this constant and you select that constant, it just makes some other constant. There's no x's over there. So my final answer would look like this: 2/3 x cubed, 1/2 an x squared, plus, who knows, some constant that, yes, was made with this little mathematical operation, but we don't care. It's just some number over there. How do you check your result? With this section on antiderivatives, with integration, indefinite integration, we always have a method of checking. You go right back to the definition. Definition says, if this really is your capital F of x, isn't it true that the derivative of capital F of x is supposed to be lowercase f of x? That is true. Now, we got to go back and remember what lowercase f of x is. So let me look back at my notes here. Lowercase f of x is 2x squared plus x. Let's check our result here. What is the derivative of this antiderivative? Let's find out. Now, we certainly remember, I hope, how to take a derivative, and you got to write it all, including the constant of integration. The 2/3 is along for the ride, no sweat there. The 3 will drop down in front, and yes, derivative. You deduct 1 from the exponent. Over here, the 1/2 is along for the ride, constant multiplier. The 2 will come down, deduct 1 from the exponent. And finally, don't forget the derivative of a constant is 0. And look at all this over here that's taking place and getting us exactly where we are supposed to be. So we do have a means of finding this thing, the antiderivative. And to do that, we need to know the rules, and we need to know the rules really well. So I'm going to review the rules with you. But in the end, whatever you do, there should be a constant of integration off the back. You don't have to show me C1, C2, C3. You can write that down if you want. In the end, pile it all together into just one constant, usually plus C. Also, when you're done finding an antiderivative, I would always take its derivative to check to see if you got it right. So in the end, when we do this indefinite integration, when we find the antiderivative, this is how I would phrase the kind of problem you're doing. I am thinking of an original function. This is capital F of x I'm holding in my hands. You don't get to see it. Whose derivative is lowercase f of x, and that's the one that you get. So I have a function. I took its derivative, and I handed you the result. And your job is to go backwards and tell me what I had. So we need to know these rules of integration, and let's go over those now. Couple rules of integration. The first important rule is this. Since the derivative of a constant is 0, we're going to go backwards now. Using the antiderivative symbol on 0, and remember, guys, you always do need a dx, well, a d-independent variable. In this case, we'll stick with x as our independent variable. Well, let me answer this question for you. I am thinking of an original function whose derivative is 0. That's what I'm thinking of right there. The derivative of a constant is 0. This is pretty much the answer key for what I'll be putting over here. If I take the derivative of, let's say, a constant times an x, you know that the constant k is along for the ride, and the derivative of x is 1, so this should be the derivative of 7x is just 7. Okay, then, what's the antiderivative of a nice clean constant? Well, let me show you a little trick over here. The k is a constant multiplier and can be put out front. It's along for the ride. And do you notice something? Do you notice the antiderivative and the d for derivative symbols actually touch each other? Boy, when they touch each other like that, they cancel right out. So what's the answer? Kx. Oh, and don't forget, always, always plus a constant of integration. Let's see. What is the derivative of x raised to a power? It's n times x to the n minus 1. So what's the integration of a power? Always bookends. You've got to have the integration symbol along with its companion dx. Well, we discussed this a moment ago. As long as it's a constant power, this has to be, n has to be a constant. It doesn't have to be an integer, but it does have to be a constant. We add 1 to the exponent, and we divide by the new exponent, and we always do put a constant of integration always after an indefinite integral. What else can we do here? We did sums and differences. We know those are pretty straightforward. But what about some trig functions? We know the derivative of sine to be cosine. That means that I should be able to integrate the cosine. Now let's read this in English. I am thinking of an original function whose derivative is cosine. What function am I thinking of? Well, the answer is right there. It's the sine function plus a constant. And you'll notice things are backwards. Everything's backwards with antiderivatives, because normally when we look at the derivative of a cosine, we get a minus sign, but the antiderivative of cosine is sine. Let's keep going. Derivative of cosine, as I just mentioned, we know to be minus the sine. So what's the antiderivative of just the sine function? Well, since everything is backwards, I would assume this to be minus the cosine. And that's certainly the case, because if you take this negative and you move it to the other side by multiplying both sides by minus 1, okay, and then actually it would find its way inside here, constant multiple can get in here, you would see the sine over here and a negative cosine over there if you move that minus over, which you can do. So the antiderivative of sine is not cosine, it's minus cosine. The antiderivative of cosine is not minus sine, it's sine. Remember, everything is backwards, including the pluses and minuses for these two trig functions. A couple more. Hopefully you remember the derivative of tangent. It's secant squared. So what is the antiderivative of secant squared? Always with a dx on the back. Integration, you must have a dx or it doesn't make sense. This doesn't make sense. You need a reminder as to the independent variable, so always have one of these. But what is the answer to this antiderivative? Again, I interpret this in English to say the following. I am thinking of an original function whose derivative is. Let's write that out, because it's important to be able to apply that to a problem. I am thinking of some original function whose derivative is blank. Now it's easy to answer if you think about it. Whose derivative is secant squared? That's the real question. That answer is tangent. So some people might look at this and say, why isn't it secant cubed over 3? You know, you add 1 to the exponent and you divide by the new exponent. That works for x's only right now. So be careful on that one. You got to answer the question. Tell me, whose derivative is secant squared? The answer is tangent, right? Whose derivative is sine? Antiderivative of sine. Let's see, the derivative of minus cosine is actually sine, because the derivative of cosine is minus sine. So everything's a bit backwards. Now that we have some of these rules in place, I think we're prepared to do a few more examples. So let me work through some antiderivative examples, and I will always test the result by taking the derivative of capital F to see if we got it right. Let's try a couple of these. What's the antiderivative of 3? Well, 3 is a constant multiple, moves out front. Remember I said, whenever the antiderivative symbol touches D for derivative, that's like matter and antimatter touching, they annihilate each other. And so the answer is just 3x. Always, please, plus a constant of integration. How about this one? Well, the 4 is just a constant multiple. Bring that out front. Okay, the antiderivative symbol looks at that power and it says, I add 1 to that power. I divide by that new power, and then, of course, always add a constant of integration. Actually, that should be a 2, sorry. 2, and then divide that. That should be a 3. So we simplify as well. How about something like this? Now remember, all of your antiderivatives have to have this at the end, and it's always going to be the independent variable. So in this case, dx. Sometimes our independent variable is t for time. In that case, that would be dt. Well, we do each one of these separately. So we do 3x squared with a dx. We do 2x with a dx. And we do cosine also with a dx. The 3 is along for the ride, so actually all we really need to do is integrate x squared over there. The 2 is along for the ride, so actually all we have to do is integrate the x to the 1 power. And nothing much I can do here until I actually execute the antiderivative. Now, 3, part of the answer. Antiderivative looks at exponents, as long as they're constant, and adds 1 to the exponent and divides by the new exponent. Plus 2. The antiderivative looks at the exponent. It adds 1 to the exponent and divides by the new exponent. Minus the antiderivative of cosine. Well, let me think. What is an original function whose derivative is cosine? That original function is sine. Now, I know each one will produce its own constant of integration, but remember, we lump them together in one big constant. In fact, these all cancel out anyway. Did we get it right? Is this truly capital F of x that we seek? Let's find out. So how are we going to find out? You know how we're going to find out. We always like to check these things by taking their derivative. So if you're capital F of x, the rules state clearly that your f prime should be the original f. In other words, the derivative of capital F of x is supposed to be lowercase f of x. Lowercase is the one that you already have. So let's try this out. Is it true, guys, that d dx of all of this is it truly equal to the original f? Now this was the original f. This is the thing we're integrating right here. So let's see if it's equal to that. And there's no constant of integration there. It's just that. It's just lowercase f. Okay, No antiderivatives. Now we're checking, so we take the derivative of 3x squared, sorry, x cubed, which is 3x squared. We take the derivative of x squared, which is 2x, minus. We take the derivative of sine, which is cosine, and finally we take the derivative of a constant, which is 0, and that would be an excellent check. They are definitely the same thing. What happens when you run into problems like this, though? Now, you should be very careful about what you do and what rules you apply. We do not have a way of integrating quotients. I'll repeat that. We don't have a method for integrating quotients. In fact, what you'll discover is there is no quotient rule for integration at all. So what I definitely do not want to see, I don't want to see f and g, f prime g minus fg prime over g squared. That's the derivative. So no quotient rule. We don't even have a quotient rule. We'll never have a quotient rule for the antiderivative. This thing, you got to get a little more creative. In fact, I think you wouldn't need a quotient rule to begin with because we would rewrite this anyway. The only rule we have is the rule that integrates x to a power. And this is just plain old x to a power. So yes, I would recommend that you rewrite this first. Now, if you do rewrite this, you can then apply the rules of integration. And you got to be careful here because you're supposed to add 1 to that exponent, not subtract. Add 1. So let's add 1. Minus 2 plus 1 is minus 1. We divide by the new exponent, and then don't forget to add the constant of integration. Now let's do some cleanup on this thing. This is just a negative quantity. It's a positive over a negative. So overall, this thing's negative. The x to the minus 1 drops down below as x to the 1, and there's no blank up here. It's a 1. And this is the antiderivative right here. Are we certain? What's the check? This is the check. Take the derivative. Now, you could, if you wanted to, use the quotient rule, but there's no need for that. Put this back up top, where it becomes minus x to the minus 1 plus a constant. And now let's really take the derivative. Well, the minus is along for the ride. We drop the minus 1 down out front, and we deduct 1 from that exponent, correct? The derivative of a constant is 0. Now the negative 1 times negative 1 is positive 1, so what we really have is x to the negative 2 plus 0, but I can make that even cleaner by putting that where it really belongs, which is down here. And we should be back to the original lowercase f of x, and we are. This is lowercase f of x right here. So I'm giving you these techniques so that you can do antiderivatives of even a fraction. But not really a rational function, not yet. We're not ready for that. But can we do this? You'll notice it's always the same antiderivative with a companion dx. That is true all the time. We must always have one of each. If you're missing this, it doesn't truly make sense. So can you take the antiderivative of the square root of x? You sure can if you put a power out there. Now, the way antiderivative seems to work is it adds 1 to the exponent, and you divide by the new exponent. And we always add this constant of integration, right? Every one of them gets one of these. Now the 2 flips up, and so we have 2x to the 3/2 over 3 plus a constant. And this thing started with a radical. I'd like you to finish with a radical. What's the easiest way to get back to a radical? Well, this right here says 3 over 2 is 1.5. So how do you show 1.5 x's? There's 1, and there's a half. Half power, that is. There's a 1 power and a half power. 1.5. It's the quickest way to go back. And there's the antiderivative of the square root of x. We're able to get even antiderivatives of radicals. Now, I did say there is no such thing as a quotient rule. I stand by that. However, you should be able to do problems like this. How is this possible to take the antiderivative of a quotient when not only do you not know a quotient rule, there never will be a quotient rule? I'll repeat that again. There is no quotient rule for integration or antidifferentiation, so don't even try it. I shouldn't see f prime, g prime. I shouldn't see tables. I shouldn't see the quotient rule. It will not work. That's derivative. If I asked you for the derivative of this, you'd say no problem. F prime g minus fg prime over g squared, and you'd work it out. Since we have no quotient rule, you simply can't do this. There is no way around this right now. But wait, there is a way around it. Each term in the numerator gets its own special copy of the denominator. And if you do that, you realize something. Luckily, these are connected by plus. This works really well when the denominator is a monomial. It doesn't work so well if the denominator is anything but a monomial. But a monomial, give each term on top a copy. You can do that, and you arrive here. Can we finish this up? Can we finish this up? Well, we can. We add 1 to the exponent. We divide by the new exponent. Over here, we add 1 to the exponent, and we divide by the new exponent. This is something for a little bit later. So we've run into a little bit of a problem here, and that's where this integration of the powers don't work for this one special power, and that's x to the minus 1. That's a topic, a whole chapter on that particular topic. So for right now, I'm going to say that it is not infinity. It's actually something else. We're just not ready for that yet. Because it looks like 1 over 0, which is infinity, but it won't be. So don't worry about that particular power of x. You won't see that until a little bit later. So maybe a better example would be this. Split it up. Remember, each integral gets its own dx. Split it up. So can you take the antiderivative of a quotient? Certainly hope so by splitting it up. That's the best you can do right now. Can you take the antiderivative of a fraction? Not really, but you can push this to the top, and that will help. Look at this one over here. The antiderivative touches the d for derivative and reveals an answer, which is x. This one we still have work to do on, but the 2 can come out front, and when you push this to the top, you get x to the minus 2, right? So we can finish this up. Add 1 to the exponent. That'd be a minus 1. Divide by the new exponent. So in the end, look what I found. Minus 2 over x. See, a positive over a negative is negative, and this deserves to be on the bottom. So we definitely want some cleanup here. Can we do even more? Yeah, we could. If we wanted to join these together, you know what the LCD is, x. So a final version of the answer could end up being this. So the reality is you can integrate fractions, but right now the only fractions that you can truly integrate are the ones that you can separate out, the ones that you can basically split. I call it a split fraction, but the thing is you want that numerator to be a monomial. Now, I want to finish up this topic of finding the antiderivative, and I want to do so by showing you that sometimes we can actually figure out what this elusive c is. So let's see if we can have an example where we actually learn or discover what c is. Capital F of x, the unknown original function, is the antiderivative of, let's make it 3x squared, and the f of 2 is 9. What that means is I don't know capital F of x yet, but this is called an initial condition. And all it says is that the point 2 comma 9 must be on capital F of x. So let's see if we can do both of these together and discover capital F of x and figure out what C is supposed to be. So first let's start with finding the general solution. The general solution again looks like this. Capital F of x equals the antiderivative of 3x squared. You know how this works now. Just like derivatives, constant multiples, you drag them out front. The antiderivative symbol looks at that squared, and what it does is it adds 1 to the exponent, divide by the new exponent, plus a c. So capital F of x is x cubed plus a constant. Just don't know what that constant is yet. Is it true? Well, the derivative would be 3 comes down, x squared plus 0. 3x squared is the derivative. So yes, that is true. That is the correct antiderivative. However, 2 comma 9 is on capital F of x. So this is the x value and y value that are on this function. So let's call this function y for a moment. Now when y is 9 and x is 2, I wonder what c is supposed to be. Solve for c, and c is 1. So I don't want you to finish there. I want you to complete the problem and tell me what the particular solution is. The particular solution that satisfies both requirements, that capital F is the antiderivative of 3x squared and the point 2 comma 9 is on that curve, is the following. It is x cubed plus c, but we discovered that c must be 1 in order to get this point, and so the particular solution, therefore, is x cubed plus 1. So the bottom line is I would practice by discovering some antiderivatives, capital F of x antiderivatives. I always ask this question. I'm thinking of an original function whose derivative is blank, the thing behind the integral symbol. I apply the rules. I add 1 to exponents, divide by new exponents. Constant multiples, you can slide them right out front. Slide them right out front. And when you see pluses and minuses, just do each one separately, but I want you to remember that every antiderivative symbol has a companion dx on the back. If you write an antiderivative symbol without a dx, it's incorrect. Also, sometimes this plus c that you must repeat over and over and over, and you'll notice this on an exam, you're going to find the antiderivative, and if you don't put plus c, I'll put a little notation. Remember, plus c, every one of them has a plus c. So sometimes you can actually learn what the plus c is if somebody gives you initial conditions. In other words, they give you a point on the curve. So what does it look like to be a general solution and a particular solution? I think we all have an idea of what x cubed looks like. X cubed sort of looks like this. And if you do x cubed plus 1, you get that. If you do x cubed plus 2, you get that. If you do x cubed plus 3, you get that. So actually, there's a whole family of solutions of x cubed plus c's. But what's the one that I wanted? I wanted the one that just happened to have this magic point, which was 2 comma 9. And that was x cubed plus 1. So x cubed plus c represents a field of solutions. It represents just an infinite number of these things. It doesn't even need to be plus 1. It can be plus 0.5, 0.25, plus the square root of 2, any constant. So you can imagine taking a curve and just shifting it up and down and filling the whole graph paper with a myriad of different solutions. Then I pick the particular solution, the one that really possesses the point of interest. And the way to do that is to discover what C is. Also, another guideline here, what if you just said integrate 7? What's the antiderivative of 7? You notice I forgot something. I forgot the dx. So, this right here doesn't have an answer. because it depends on what I put back here. If I put dt, they cancel because they touch. That's the only time they cancel. The answer is 7t plus a constant. So see, the answer might not be 7x. We don't know the variable, the independent variable that we're taking the antiderivative with respect to. So remember, the dx, dt, ds, whatever it is, has to be on the back as a reminder, and then we'll know the variable. Now, normally we do know the variable of integration because it's part of the problem, but that one there were no variables, so we didn't know what it was. But I put a dt on the end. I said, nope, this problem must have had something to do with time. And so it's the derivative of 7t is just 70. Sorry, 7. So that's it for section 4.1. A lot to think about. It's a brand new topic for you. It's going backwards, which is always harder. But the rules are clear. The antiderivative of a constant is going to be that constant times the variable of integration. In other words, the antiderivative of 7 is 7t or 7x or 7s. The antiderivative of a variable raised to a power, what do we do? And it can only be a variable right now, not anything else. There's no chain rule yet. So the antiderivative of t to the 4th power, dt, as a reminder, would be t to the 5th over 5. Just got to remember how to do that. The antiderivative of a sum or a difference. Luckily, we do each one separately. They don't interact with each other, so just I would write them out separately and then work on each one. Constant multiples come in front. They stay right in front. And we got to know the antiderivative of our trig functions. Remember, everything's backwards. So the antiderivative of secant squared is tangent, because somebody took the derivative of tangent. The antiderivative of cosine is sine, because behind us somebody took the derivative of sine to produce cosine. And the antiderivative of sine is minus cosine, plus c every time. And the only time I can figure out what c is somebody gives me a point on that curve. Well, sorry this went on so long, but it's a new topic and it's worth extra coverage here. And I hope that you really dig into the homework problems. And let me know if you have any questions at all, if you need help with it. Thank you. Good luck.